continue with it today. Okay, so we defined simple harmonic motion. In fact, we saw that simple harmonic motion is a subset of oscillatory motion. So under oscillatory motion, we have periodic motion, which is also an example of oscillatory motion, and then simple harmonic motion is the daughter of oscillatory motion. Now, what is oscillatory motion? We define oscillatory motion as a motion as a to and fro or up and down motion of a body about a fixed point. Okay, the repeated up and down or to and fro motion of a body about a fixed point. That is oscillatory motion. Then we also define what periodic motion is. And periodic motion is the motion of a body that takes place within a fixed time interval. So an example of periodic motion, we made mention of the motion of the sun, the earth around the sun. You know, it takes 365 days for the earth to move around the sun. And after 365 days, the motion is repeated. Okay, so the sun is in the middle. Please, Darius, mute yourself for us. The sun is in the middle, earth is here. The earth will take 365 days to move round the sun. And after the 365 days, the journey, the same time, or the same journey is had repeatedly. Okay, and in periodic motion, the same distance is taken over and over. So the motion of a body that takes place within equal time interval. The motion of a simple pendulum, and a lot of examples were mentioned. Then we looked at simple harmonic motion, SHM. And we define SHM as the motion of a body, the repeated to and fro or up and down motion of a body whose acceleration is directly proportional to the displacement, but oppositely directed, meaning that when a body is executing simple harmonic motion, the acceleration A must be directly proportional to the displacement Y or X, but it must be oppositely directed, meaning if the acceleration is positive, displacement is negative. Their directions always opposes one another. And so if you are saying that a motion of a body is simple harmonic, ladies and gentlemen, we must see this. We must see the acceleration of a body being directly proportional to the displacement, and the direction of the two must be oppositely directed. And this characterizes simple harmonic motion. Okay. Examples. We made mention of several examples. The motion of a simple pendulum, the motion of a bifilar suspension, the motion of a compound pendulum, the motion of a cantilever suspension, the motion of liquid in a U-tube, the motion of electrons within a conductor, the motion of pistons in an automobile engine, and the motion of the loaded spring, the motion of a test tube placed in a liquid, a loaded test tube placed in a liquid, and several examples. Then we looked at the relationship between simple harmonic motion and circular motion. And then here we saw that if a body is executing circular motion, then the body is also, the shadow of the body or the same body is also doing simple harmonic motion about a fixed point O. And so we saw one complete revolution of a body and then derived the displacement graph for one cycle out of it. We saw that the displacement or the position of a body executing simple harmonic motion at any time t at any angle can be determined by a sine theta. This is displacement with respect to angle. And because theta is equal to omega t, this same equation was remodified to be y is equal to a sine omega t. And this we saw to be the displacement equation of a body executing SHM with respect to time. So this equation is with respect to angle, and this is with respect to time. Then if the oscillation is along the horizontal, please, y denotes that the oscillation is vertical. If it's along the horizontal, we came up with the equation x is equal to a cos theta, or x is equal to a cos omega t. Class, I hope you can hear me. Class, I hope you can hear me.
Yes, sir.
All right.
Yes, sir.
Then we saw key terms as what do we mean by displacement in simple harmonic motion. And we define displacement as a position of a body from the main point. Okay? Or yes, the position of the displacement is a position of a body executing SHM from the main point. The amplitude, we saw that to be the maximum displacement. Period is the time taken to make one complete cycle of a wave. Then the frequency, the number of complete cycles within a given time. So we plotted the displacement equation of a body executing simple harmonic motion with respect to angle. We did that for one cycle, and I gave you the assignment to do it for 3 complete cycles. So if you recall, this graph was vertically displacement y against angle, but today we want to plot the same graph using time. The time taken for an oscillating body, if there's the mean point, to move up and down about a fixed point O. You know, a complete cycle is made up of four quarters, moving from the mean point to one extreme, from one extreme back to the mean point, from the mean point to the other extreme, and then returning. So the time taken to do that, we said, is the period. The time taken to make one complete cycle or oscillation is the period. Since a complete cycle is made up of 4 parts, 1 going up, 2 coming down to the main point, 3 moving to the other extreme, and then 4 coming back to the main point. The period will be divided into 4 parts. Quarter of the cycle t. Don't forget, in terms of angle, this was 90. Then 2 quarters or half of the period Then we have 3/4 of the period. We are dividing the period into 4 parts because a complete cycle is made up of 4 equal parts. Please, are you with me? Class, are you with me on the time? All right. So we are plotting this, okay, using vertical oscillation. So we want to use the equation y is equal to a cos omega t. So what is the vertical as sine omega t? We can also plot it with cos, and that would also be given to you as an assignment over the weekend. So when t is equal to 0, when we are here, when t is equal to 0, what will be the displacement? Y would be equal to a sine omega times 0. Any number times 0 is 0. So we have a sine 0. Since sine 0 is equal to 0, meaning at time t is equal to 0, the displacement y would be equal to 0. So this time would give us a displacement y of 0. Any oscillation occurs between two extremes. So let's indicate the amplitude. The maximum oscillation and then minus amplitude, meaning the oscillation will take place between the positive and negative. Okay. Now when t is equal to quarter of the period, what will be the displacement? Yes, class. When t is equal to quarter of the period, what will be the displacement? Can any one of you calculate that the displacement when t is 1/4 of the period? Class, when t is equal to quarter of the period. All right, let me do that for you. So you do other time or other, yes, given time. So y is equal to a sine omega is equal to 2 pi over the period. And we are given t to be equal to quarter of the period. So t over 4. Okay. So we have the period canceling this period, 2 going into 4, 2. So we have y is equal to a sine pi on 2. Class, change pi on 2 to degree. What is pi on 2 in degree? Pi on 2. Change that to degree. Anybody can answer, please. Pardon? Oh, I can't hear you. Pi over
180.
2. No, pi over 2 in degree. Pi is 180.
90.
It's 90. So we have a sine 90 degree, and sine 90 is 1. So y will be equal to a, meaning that at time t is equal to quarter of the period, the displacement will be equal to the maximum value, the amplitude. It's just the same thing as when we use angles. Now, when t is equal to 3/4 of the period, what is the displacement? Please calculate that for me. Calculate that and then give me the answer to plot. When the time is equal to 3/4 of the period, what will be the displacement y? You can look on this particular one, the second time, to aid your calculation. When t is equal to 3/4 of the period, what will be the value of the displacement class y? Is anyone ready? Yes, if you are ready. Pardon? Yes, Ronnie and Kwa, I'm listening. Ronnie. Put your values into it. If you are not following, please watch carefully. So when the time is this, you have a sine omega is 2 pi over the period, and the time t is equal to 3/4 of the period. Class, watch carefully. So t would cancel this t, 2 would cancel this. So you have a sine 3 pi over 2. Change 3 pi over 2 in degree. Nathaniel, mute yourself.
270.
That is 270. So you have a sine 270. Class, what is sine 270?
-1.
-1.
Oh, I get you. We jumped the time. You see, we're dividing the time into 4. So half, quarter of the period, the next must be half. Oh, but I repeated 3/4. Hey, you have eyes and you can't see. So this is actually half. Then 3/4. And then the full period. So the time must actually be a half of the period. Okay. Sorry for the. So t must be half of the period, not with 3/4. We haven't gotten to 3/4 yet. That is why, Ronnie, you were talking about negative half, -1. Okay, so this is t on 2. So this and this can cancel out, and we have y is equal to pi on 2. Pi on 2. And pi on 2 is 90. I said pi on 2. It will be pi. Let me take my time to. So it will be pi. 2 would cancel this 2. T would cancel t. And so we'll be left with sine pi. And pi is 180. So we have a sine 180 degree. What is 180? Sine of 180. What is sine of 180?
0.
That's 0. So at time t is equal to half of the period, the displacement is 0. Then 3/4, we have solved it, and we realize that it will be equal to the negative of the amplitude. So let's plot that without wasting time. Because we have already solved for 3/4, that is why. Then when t is equal to t, the whole period, what will be the displacement? Please do this for me. When t is equal to t, when t is equal to the period t, what will be y? Yes, Frida. Efia, you are also here. Elsie, yes. Whoever is ready.
0.
That will be 0. So when we join, we have this. For one cycle. Okay, so this is the displacement graph in terms of time for one cycle. We've done it for angles as well, so please take note. If you have any question, ask. All right, if you don't have question, let's continue. So we see the body's displacement changing with time. At a point, the body's displacement is 0. At another point, the displacement is maximum. At another time, it falls back to 0. At another time, it increases in the opposite direction. So the displacement of the body is changing with respect to time. And class, when you have a body whose displacement changes with time, what does this change result in? If a body's displacement is changing with respect to time, what will this result in? Yes. Yes, anybody? Change in displacement with respect to time.
Acceleration.
Displacement with respect to velocity. Okay, don't forget velocity is y, change in y over t. It can also be changed in t. So when we draw vertically, if this is the mean point, O, the body is in motion, up, down, down, up, down. See, this is the repeated up and down, or to and fro horizontally. And if a body is moving in such a way that it is constantly moving, okay, in this manner, then we can talk about its velocity, because the position is changing with respect to time, and so we can identify the velocity of the body as its position changes. So the next area of interest is this: velocity of a body executing simple harmonic motion. Velocity of a body executing simple harmonic motion. And why velocity? So let's give ourselves this question and answer. Why velocity? Or why velocity equation? We are looking for the body's velocity because this is because the body's displacement changes repeatedly or periodically with time. Or this is because, hey, I've omitted a lot of. So this is because the body's position or displacement changes repeatedly with respect to time. So if you are quizzed why you are to determine the velocity of the body doing simple harmonic motion, it is because the body's displacement is changing periodically or repeatedly with time. And when a body is moving in such a way that its position or displacement changes with time, it amounts to velocity. So V is equal to dy over dt, where this is change in velocity, change in displacement change in displacement over change in time. Okay. This also means that if we want to find the velocity of the oscillating body, we should differentiate the displacement function with respect to time. So velocity is equal to the differential of the displacement, and we are looking at vertical displacement. Please, Frida and Elizabeth and the rest of you, it can also be horizontal displacement. So I am looking at vertical change in the vertical displacement. So y. So I'm going to substitute a sine omega t and then look at the change with respect to time. So please, if you are doing looking at how the body is changing position with respect to time, you use a sine omega t. If you are looking at how the body's position changes with respect to angle, then it will be dy over the theta. And so here v would be equal to del into bracket a sine theta divided by the theta. Okay, change in angle. You cannot use time, the t, when you have that in angle. It doesn't work like that. Okay. Now, once you haven't done differentiation in mathematics, please, I'm going to do it and then give you the final results. When you grow in mathematics, you understand. Okay. So class, yes, I know it's new to you. You are informed too. You haven't done differentiation. But physics, we must apply. So I'm going to give you the formula for when you differentiate this. Later on, if you do it, I can have the time to explain to you. So when you differentiate a sine omega t, it will be equal to a times omega times cos of omega t. Okay, when you differentiate this, what is within the bracket, this is what you must get. This is what you must get. So the velocity function of a body executing simple harmonic motion along the vertical is equal to the product of its amplitude and its angular velocity and the cosine of the angular displacement expressed in time. I'm sure the question on the mind of some of you is that, can we multiply omega and this omega to get omega squared? No. This is because if you have a trig function, example, 30 or 3 times 45 times cos of 45 degree. Please, what is here is the same as theta. Don't forget I said theta is equal to omega t, meaning that the body is moving with uniform angular velocity. So when you have this, can you multiply 45 degrees by this 45? Class, can you do that?
No, sir.
So you cannot multiply this omega by omega here. It is a conjoint thing. This is omega t, which is equal to the angular displacement. So when you differentiate displacement along the vertical with respect to time, this is what you must have. Okay, this is what you must have. The velocity will be equal to its amplitude times angular velocity times the cosine of the angular displacement. Please, this is the velocity equation with respect to time. With respect to time. What is the relevance of this equation? When you are given any time, at any time t, calculate the velocity. This is what you will use to do your calculation. If a body is executing SHM and you are asked to calculate the velocity of the body at any time t, this is what you would use for your calculation. Okay, now V is equal to A omega cos omega t. Look at the displacement function. Look at the displacement function. What name do we give to this letter A? What is A? What is A here? Yes. What is the A here? Yansabua and Co, please, let's hurry up with the response. What does the A here represent, class?
That is the amplitude.
And the amplitude is the maximum displacement. Yes, okay. So with the velocity, this is the maximum V maximum, the maximum velocity of a body executing simple harmonic motion is equal to its amplitude times its angular velocity. So A times AW or A omega is the maximum velocity of an oscillating body. Please, is there any question? It's a bit technical. When we start solving problems with it, you understand. So A omega is the maximum velocity. Okay. So as I said, at any given time t, you can use this to calculate for. You can use this to calculate for the velocity. So this is the velocity equation with respect to time. Now, if I'm given displacement, y to calculate for velocity, how do I do it? Please pay attention very well. Let me drop attendance on the page because a lot of you are absent today. So with this, if at any given time t, I can use this to calculate for the velocity. So I have velocity equation with respect to time. If I'm given displacement y or x to calculate for velocity, how do I do it? So we are going to play around this equation. You and I are going to play around the velocity equation in terms of time. A omega cos omega t. To get equation in order to represent velocity in terms of displacement y. So example, let me create a situation for you to understand. A body is oscillating. This is the mean point. I'm told that the body is here. The position of the body is here. So if I'm told that this distance from the mean point O, this distance as y is equal to 2 centimeters. To calculate the velocity of the body whilst it is here, how do I do it? Here I'm giving displacement y to find v. So I need to have an equation connecting velocity to displacement in order to do this. What I have so far, this equation connects velocity to time. So at any given time t, I can use this to find the velocity. But what about y? So that is the essence of what we are going to do. Mamiya, Eva, Frida, Rachel, and the rest of you, are you there?
Yes, sir.
Yes, sir.
Okay. How do I play around this? Class, if I write this equation as the square root of a squared omega squared cos omega t all squared. Class, have I changed anything? Have I changed anything from this original value?
No, sir.
The ladies are not responding. If I rewrite this is 1. If I write equation 1 as this, equation 2, have I changed equation 1? Ladies, let me hear your voice. Have I changed equation 1? Hey, they are still not there.
No, please.
All right.
No, please.
If no, then yes can divide. Okay. If no, then I can decide to write this as when I take the square root of omega squared and then the square root of a squared cos omega t all squared. I hope I haven't also changed anything, right?
Yes.
Yes, sir.
Okay. The square root, what is the square root of omega squared? What's the
Omega.
That's omega. This times A squared times cos omega t all squared. I haven't still changed anything. However, Mr. Hackman, okay, I don't know if you've done trigonometry, but I'm sure Mr. Hackman has taught you that if you have sine squared of any angle plus the cosine squared of that same angle, this is equal to 1, isn't it? Isn't it? Yes.
Yes,
if you,
please.
if you won't respond, I'm responding it for you. Yes. Okay. So I want to make cos squared theta the subject. And this is equal to 1 minus sine squared theta. Don't forget, theta is equal to omega t. So I want to modify equation 3. Okay, wherever I see cos omega t squared, I'm going to put 1 minus sine squared omega t. So V therefore is equal to omega out times a squared times 1 minus sine squared omega t. I'm just substituting theta for omega t. Class, are we fine with this? Are we okay with this?
Yes, sir.
Please,
Yes.
sine omega t squared is the same as writing sine squared omega t. The value is the same, even though we have done redenomination. Okay, so V is equal to omega. I want to multiply through by the a squared outside the bracket. So I have a squared minus a squared times sine squared omega t. And I can rewrite what I have as a squared minus, I want to put everything within the bracket, a sine omega t all squared. Okay, so look at how I'm carefully developing, playing around this equation. Now, because I know that the displacement equation along the vertical of an oscillating body is equal to, I have y is equal to a sine omega t. Francis, please give me a minute. I'm at home. Please, you can come over. I'm at home. All right. So if y is equal to a sine omega t, then V would be equal to omega times a squared minus y squared. I'm substituting y for a sine omega t. Please, are we fine with this equation? Are we okay with this?
Yes, please.
Yes, sir.
Good. Now, what have I achieved? I have got love.
Sir, please, the sine omega t squared. How is it possible that is sine is equal to sine square omega t. Because if the square is outside the bracket, then it should affect everything that is inside.
I got to come again.
I'm asking that why is it that the square of the sine omega t, when you expand it, it's affecting only the sine,
Oh,
but it's not
it's
affecting
God
the
love. It's just skills that we use, but ideally, sine omega t all squared. It is we actually write it as sine omega t, but we want to remodify it, redefine it, and that is why we write it as sine squared omega t. So it's a scale we seems to have adopted. Is that okay?
Yes, sir. So it
But
means you are not following the main.
ideally, it should be it should be this, the left hand side one.
Okay.
We just
Yes.
want to be skillful. Okay.
Okay. Thank
All
you.
right. So what we have achieved is this. We've succeeded in getting velocity in terms of displacement. Don't forget, for a body executing simple harmonic motion, omega is constant. That is the uniform of SHM. A body doing SHM. So omega is constant. The amplitude is also constant. Whoever is doing the oscillation decides the magnitude of the amplitude. Okay, so omega is constant. A is also constant for an oscillating body. Therefore, we have V would just be directly proportional to the square of that. So this equation, V is equal to omega. This is the velocity of a body executing simple harmonic motion in terms of displacement. Velocity in terms of displacement. So when you are given at any displacement or position of the body, you can be able to calculate for its velocity as well. Please, if you have any question, ask me before we put this into test, or we apply this in solving problems. Yansabuakwa, any question? Goslav, any
No, sir.
question? Mamiya, Eva, Rachel, Rachel. Okay. Let's apply this in solving a question. The problem solving would bring clarity to what we have just done better. So we have displacement, velocity in terms of time, and velocity in terms of displacement. Okay. Please, let's put down this question. An object attached to a spring oscillates in the vertical plane. About a rest position O. An object attached to a spring oscillates in the vertical plane about a rest position O with an angular velocity omega equal to 4 radian per second. I said for an oscillating body, angular velocity is constant. So with an angular velocity 4 radian per second, and amplitude equal to 10 centimeter. So the amplitude is also constant and is given. And amplitude 10 centimeter between extreme positions A and B. So it is oscillating vertically. This is the rest position is O, and it is oscillating between extreme positions A and B. So it's basically moving up, down between A and B around the mean point O. Calculate I, the velocity when crossing the rest position or the mean point. Calculate I, the velocity when crossing the rest position. Calculate I, the velocity when crossing the rest position. II, the velocity at the extreme ends A or B. II, the velocity at the extreme ends A or B. And III, the velocity at a point 6 centimeter from O. The velocity at a point 6 centimeter from O. So let's even assume from O, the oscillating body is here. If from O to its current position, we are told that the displacement is 6 centimeter. So basically, we are asked to determine the velocity of the body at this position, which is 6 centimeter from O. Okay. So the velocity when crossing the rest position. The velocity at the extreme ends A or B. The velocity at a point 6 centimeter from O. This is the problem of the afternoon. So let's try it. And I'm going to do that with you so that later examples will be given to you to take a bite. So the question seeks to determine the velocity of the oscillating body, okay, when various displacement or positions of the body are given. So question 1, we are to determine the velocity when crossing the rest position, I. Now class, what is the displacement of the body when crossing the mean point? When the body is just crossing the mean point, what is the displacement y of the body? Yes. When the body is just crossing the mean point, what is the displacement y of the body? Yes, anyone to share what he or she thinks with us? This is the mean point. O. So when the body is over here, just before it crosses, what will be the value of the displacement of the body? Yes. Anyone to share what he or she thinks with us. When the body is just crossing the mean point, what is its displacement? Fifi Pepra, I put it to you. What will be y at the mean point? Oh, Fifi. Mommy, Mommy, are you there? Mommy, hey, everybody is quiet. Okay, Elizabeth.
Yes, please.
What is the displacement of the body when it's just crossing the mean point? As at when it just crosses the mean point.
Please,
Why?
I think it's
Mhm.
0.
It is 0. When the body is just at the mean point, it has no displacement. Okay, its position with respect to the mean point O is the same, so there is no displacement. So because at the mean point y is equal to 0, when you put y equal to 0 into the equation, you have v is equal to omega times the square root of a squared minus 0 squared. And 0 squared, the value is the same. So you have omega times a. Class, for an oscillating body, its maximum velocity, and I have said this earlier, its maximum velocity always is equal to omega times a, and it occurs whenever the body is just crossing the mean point. So maximum velocity occur when crossing the mean point or the rest point or the equilibrium position. Okay, so what is the expression for the maximum velocity? Is omega times the amplitude. And where does it occur? The maximum velocity always occur at the mean point. Do not forget this. Do not forget this. So when the velocity when crossing the mean point will be equal to omega, which is 4 radian per second, times the amplitude, which is 10 centimeter. So the velocity when crossing the mean point is 40 centimeter per second, which is also the same as 0.4 meter per second. So this answers the I question. Class, are we okay with the solution?
Yes, sir.
Question 2. The velocity at the extreme ends A or B. The velocity at the extreme ends A or B. I want you to calculate this for me, and I'll call one lady to answer, give us what she had as the answer, and a gentleman to do that. So determine the velocity at the extreme. Just look at how I solved the I question. And then give me velocity at the extreme ends, A or B. I'll take the answer of one gentleman and one lady. So get ready to share. Let me go through the roll call. I have Frida here. If I'm calling you, get yourself. Adoma is here. Ahmed, Bilal, you are also here. Asidachi, you are here. Bernard, you are here. Deram, you are here. Elsie, I've seen you. Elsie. Efia, Elizabeth, Fifi, Frida, Frederick, Glenn. Glenn, you are here. God love, Isaac, Joel, Joe, you're also here. Julian, you are here. Cadwell, KB, Kelvin, another Kelvin, Leonard, Aqua. Hey, Leonard Aqua. Leslie, Michelle, Michaela, Nathaniel. You are also here. Yansabuakwa has been talking. Otukono, you are also here. Oreku, Rachel, Ruben, you've also been hiding. Nana Safo, and Willis. So I can call any one of you. All right, I think you must be through by now. So, Rachel, are you there? Hello, Rachel. Hey, Rachel will not talk to me. Okay, Jojo, let me hear from you. What do you think is the velocity of the body at the extremes?
I believe that the velocity at the extremes will be 0 meters per second.
Why do you think so?
This is because at the extremes, the amplitude will be equal to the displacement. So when you put it,
yeah, correct for 3 points. Okay, so when the oscillating body gets to the extreme, the displacement is just equal to the amplitude. So at the extreme, y is equal to a. And if y is equal to a, v would be equal to omega times a squared minus y squared. And if y is equal to a, when you substitute this into the equation, you have a squared minus a squared, which is 0. So the minimum velocity of a body executing simple harmonic motion occur at the extremes, whilst its maximum velocity also occur at the mean point. And the minimum velocity is always 0. Minimum velocity is always 0 and occur at the extreme. Okay, class, make me proud with question I. Calculate the velocity at a point 6 centimeter from O. I. Calculate velocity of the body at a point 6 centimeter from the rest point O. Start work. I've guided you, so let me see what you can also do. Yes, back to the cubation trap. What are your answers? What are your answers for velocity when at a point 6 centimeter from O? Let me hear from you, Frida. Give me your answer. Frida.
Please, 32 meters per second, centimeters per second.
32 centimeter per second. Okay, Yansabuaka. Yansabuaka. Hello, Yansabuaka. Oh, he's not there.
Service, I had 12 meters per second.
Okay, so Nyansabuaka also had okay 12 meter per second. Last answer from Rachel cannot hear me. She has gone home. Elizabeth.
Mr. Elia, please, I'm not done. I'm not getting it.
Okay. Jojo, are you true? Okay. Nyansabuaka.
Please tell me
Service
to
is
I'm
32
true.
meters per second.
32. Please.
Okay, Nyansabuaka, you are in to change your answer. You had 32. Okay. Let's see.
Yes, sir.
All right. Let's see. So V is equal to omega times A squared minus Y squared. So we have 4 radian per second. The amplitude 10 centimeters squared. So 10 squared minus 6 squared. So you have 400 minus 36. And what is 100 minus 36? What is 100 minus
64.
64? What is the square root of 64?
8.
So you have 32 centimeter per second or 0.32 meter per second. You can also decide to change everything to SI units. Okay, so 10 centimeter would be 0.1 minus 6 centimeter would also be 0.06 squared, and you have 0.32 meter per second. So this is how to work out velocity whenever you are given displacement. Now we can, you see, we plotted a displacement graph for one cycle. We can also plot velocity graph for one cycle. We can also plot velocity graph for one cycle. And let's quickly do that. So whenever you are plotting a graph, then you must use velocity with respect to angle or velocity with respect to time. And we are always looking at oscillation along the vertical. So we are using the equation V is equal to A omega cos omega t. We just saw that the maximum velocity is a omega. So the oscillating body will just be oscillating between this. So minus a omega. So let's do this in terms of with respect to time. So V in meter per second, and then T slash second. So at a time, please give me a minute, I'm coming in. Okay, so whether displacement, velocity, or acceleration, okay, the time taken to do that is a period. And a period is made up of 4 quarters. So let's divide the period into 4 parts. So quarter of the period, half of the period, 3/4 of the period, and the full period. It's just similar to going on circular motion from 0 to 90, 90 to 180, 180 to 270, and 270 to 360, the same thing. So we can even plot this in terms of angles. A omega cos theta. A omega cos theta. And here we'll plot it in terms of so it's just the same thing as we have done. Let me check. Okay, Leonard. Now, so this is the equation that will be used for this graph. Now, class, when t is equal to 0, when t is equal to 0, what is the velocity? The same thing as we use when we're plotting the displacement graph. When t is equal to 0, what will be v? Can somebody work this out for me? When t is equal to 0, what will be v? Jojo, Yansabwa kwa, Fifi, Frida, Rachel, when t is 0, what will be v?
0.
Sorry, look at it again. Look at it again.
Please, 1.
So 1 times a omega. Okay, so when it will be equal to the positive amplitude, let's work it out for the benefit of us all. So we have v is equal to a omega times cos of, if t is 0, omega times 0 would be 0. And cos 0 is equal to 1. So you have A omega times 1, which is equal to A omega. So when t is equal to 0, the velocity will be equal to the maximum positive value. Please, are we okay?
Yes, sir.
All right. So when t is equal to quarter of the period, what will be the velocity? Yes. Work it out and tell me.
0.
No, okay. Yes, it's 0, but I want the rest of you to also work. Yes, it's 0, but let's work it. So we have V is equal to A omega cos 2 pi over the period times omega times the time. The time is t on 4. T on 4. So when we multiply this, we have this and this canceling out. 2 going into 4, 2. So we have A omega cos of pi on 2. And what is pi on 2? What is pi on 2 in degree?
90 degrees.
90.
So we have A omega cos 90. And since cos 90 is 0, it means at this time, the velocity will be 0. All right, so I'll leave t is equal to half of the period for the ladies to solve, and then the gentlemen work out for t is equal to 3/4 of the period. So ladies, yours is when t is equal to half of the period, and gentlemen, yours is t is equal to 3/4 of the period. T is equal to t is for Mr. Abia. So start work. And I'll call any of you, the ladies, to respond because it's for ladies. Yours is t is equal to half of the period. So ladies, this is your time. T is equal to half of the period. Then the gentleman, yours is t is equal to 3/4 of the period. And Mr. Abia, maybe Mr. Abia cannot solve it, so I'll give it to one of you. So any one of you must prepare. Ladies, are you ready? The velocity when t is equal to half of the period.
Very nice. Good.
Yeah. Ladies, are you ready?
Yes.
Let me hear from any one of you. What's the velocity at that time? Yes. Who is talking? Yes, Frida.
Please, I had negative AW.
Okay, so negative of the maximum value. Okay, Frida. Negative of the maximum value. Ladies, thank you. So this is the point. Gentlemen, T is equal to 3/4 of the period. What is the displacement? Velocity.
The place is 0.
Okay, so 0. Miss Abia cannot solve hers. So I'll give it to the girls to do that for me. And I'll call on Elsie and Efia. Elsie and Efia, work this out for Miss Abia. T is equal to the period. What is the velocity at T is equal to the period? Elsie and Efia. Please, the rest of you must also work it out, okay? Yes, Elsie, are you ready? Efia, are you ready? Okay, anybody who is ready to share with us? Anyone who is ready? Yes, Elizabeth.
Please, I had A omega.
So the maximum A omega is the maximum velocity. Okay. So Elizabeth, next time say it as it's equal to the maximum velocity.
Yes, please.
So thank you. So let's then join the points. It's a curve. It has a turning point. So when you are drawing it, let's see the turning point. So class, this is the velocity graph of a body executing simple harmonic motion for one cycle. Velocity graph of a body executing simple harmonic motion for one cycle. Okay. Please, is there any question? All right. So, what do we see as the body oscillates? We see its velocity changing with time. It is maximum when crossing the mean point O. The velocity is maximum whenever it's crossing the mean point, and it is minimum at the extremes. Okay, it is maximum whenever it's crossing the mean point, minimum at the extreme. So look at something. If this is the body is doing vertical oscillation around O, when the body is crossing the mean point, it is crossing it with that maximum velocity. When the body is going up, let's assume the extreme one extreme point is here, A. Another extreme point is here, B. It has maximum velocity at the mean point. When it is going to the positive extreme, what do you think is happening to the velocity? Is the velocity increasing or decreasing? When it's going up to the positive to A, is the body's velocity increasing or decreasing? Class, I'm waiting for your response. When the body is from the mean point going to the extreme point A, will the body's velocity increase or decrease?
It will increase.
Answer Boakwa. Look at it again. We just saw that the body has minimum velocity, specifically 0 at the extremes. 0 at the extreme point A and B. It has maximum velocity whenever it is crossing the main point. So when it is going up, will the velocity increase or decrease?
Decrease.
It is decreasing because maximum, it must decrease. By the time it gets to A, it has decreased to 0. Then when it is coming back to the mean point, what do you think will be happening to the velocity? Will it increase or decrease when it is coming from A to O?
Increase.
It would increase. So by the time it crosses O, it crosses it with the maximum velocity. When it's coming to the other extreme, what will happen to the velocity? When it's coming to the other extreme point B, what will happen to the velocity? Obviously, it must decrease. So we have 0, increase. By the time it comes to O, maximum, decrease to 0, okay, and increase again. So we see the bodies, as the body oscillates, its velocity is changing with time. If we have a kind of motion whose velocity changes with respect to time, what will this change amount to? When velocity changes with respect to time, what does it amount to?
Acceleration.
Acceleration. So the acceleration function or equation of a body executing simple harmonic motion, just as we saw for velocity. So the question is, why acceleration? Acceleration because we see the body's velocity changes periodically with time. So that is why we are looking for acceleration of the body executing. Okay, that's the reason for us looking for the acceleration of a body doing simple harmonic motion. Acceleration is equal to change in velocity with respect to time. Mathematically, we call this as dv on dt, the rate of change of velocity with respect to time. So it means that before we can determine acceleration, we must differentiate the velocity function with respect to time. And what's the velocity function? A omega cos omega t. Don't forget the velocity function with respect to time. We had A omega cos omega t, vertical oscillation. So the differential of this, okay, would also give us A omega. In differentiation, the coefficient is not affected. Then you differentiate omega t with respect to time. This will give you omega times, when you differentiate a cosine function, it gives you negative sine function. So the differential of, Chris, please mute yourself. The differential of cos omega t is negative sine omega t. Okay, so when we put them together, we have minus omega squared a acceleration. So acceleration A, amplitude A. So let's use capital A for the amplitude in order to create that distinction between acceleration and amplitude. So minus omega squared, this A, sine omega t. Class, this is the acceleration function with respect to time. Acceleration equation or function with respect to time, meaning at any given time, you can use this to find the acceleration of the body. Now, if I'm giving displacement to find acceleration, how do I do it? Just as we did for velocity. This time around, it is so simple here because we don't need to play around this equation so much to get y into it. Because this part is equal to the displacement equation of a body executing simple harmonic motion. Remember, we had y to be equal to a sine omega t. So what I've put within or clouded is a, which is displacement. So it means that a is equal to negative omega squared times y. This is the acceleration equation with respect to displacement. So at any given displacement, you can use this to calculate for the acceleration of the body. Okay. And the acceleration is very, very important because look at something. Omega squared is constant. Omega squared is equal to a constant. So if omega squared is constant, then A is directly proportional to negative of y. Okay, and this is what defines a body doing or executing simple harmonic motion. Because when we started, we said that whenever a body is executing simple harmonic motion, its acceleration is directly proportional to the displacement, but oppositely directed. So our acceleration equation confirms that yes, we are going through or doing simple harmonic motion. Okay, so the acceleration equation or formula for a body doing as simple harmonic motion is given by minus omega squared y. Let me give you 5 minutes break to return. I think usually I should give you this, but it usually escapes me. So 5 minutes water break and we continue. It's 4:38. So 5 plus 38. Okay. 43, you are coming back. So water break. Okay, so hello, back from commercial break. Okay, so the acceleration equation in terms of time, acceleration equation in terms of displacement. Look at the question we just solved. An object attached to a spring oscillates in the vertical plane about a rest position O with an angular velocity of 4 radians per second and amplitude the same, the question we just solved. Let's calculate its maximum. I'm adding 2 questions to it. So IV, we ended at III. IV, we are to determine the maximum acceleration. The maximum acceleration. Maximum acceleration. And V, the minimum acceleration. Hello, are we there? Are you there? Asada, Bilal, Elsie, Elizabeth, and Co. Can you hear me?
Yes, sir.
Okay. So look here. If acceleration is equal to minus omega squared y, class, where do you think maximum acceleration would occur and minimum acceleration would also occur? Let me hear from you. Where would maximum acceleration occur? Anybody? If acceleration is equal to negative omega squared y, where would maximum acceleration occur and minimum acceleration also occur? Yes, Nathaniel. Nathaniel. Oh, Nathaniel, I'm listening.
Sir, please, I'm not answering the question, but it seems your line is breaking, or it's me.
I think, please, is it a general problem that my line is breaking to all, or it is?
So your line is still breaking.
But is it better now? Rachel, is it better?
Sir, please, I was saying your line is breaking. Seriously.
Oh, I think it's a network problem. Class, is it better now? Can you hear me now? Hello? Hello? Oh, we are almost ending the class. Hello? Can you hear me?
Not clearly.
Okay. I wish. Okay, can you rejoin? If it's better, let's continue. If it's not okay, can you rejoin?
Okay.
Please, it's better.
Okay. All right. All right. So where would maximum acceleration occur and where would minimum acceleration also occur? That's the question on the table. If acceleration is equal to this, where do you think maximum acceleration would occur? Rachel, can you help? Hello, Rachel, can you help? Jojo. Hello, Jojo. so sad. I don't know if you. Class, can you hear me? That's right. Hello. Hello.